Right now, as you sit there watching this, you are also walking through walls. You are also orbiting Jupiter. You are also traveling backward through time to the moment of your birth. This is not metaphor. This is not poetry. This is what the equations of quantum mechanics actually say. Well, and here is the strange part. The physicist who figured this out, who showed us that particles genuinely explore every conceivable path through the universe simultaneously, was not some detached mystic. He was Richard Feynman. What he discovered does work. It predicts experimental results with stunning precision. It underlies every calculation physicists make at particle accelerators, like the Large Hadron Collider. And yet, what it tells us about the nature of reality is so bizarre, so counterintuitive, that even Feynman himself admitted nobody truly understands it. The idea is called sum over histories. And once you grasp it, you will never see the world the same way again. Let us start with something familiar. You throw a ball. Where does it go? Classical physics has a simple answer. The ball follows a single definite path. It arcs through the air, obeying gravity, and lands in a predictable spot. One ball, one path, one history. This picture served humanity well for centuries. Newton built it. Engineers relied on it. It works beautifully for baseballs and planets and everything at the human scale. But then came the 20th century, and everything fell apart. In 1926, Erwin Schrödinger developed an equation describing how quantum particles behave. It treated particles not as tiny billiard balls but as waves, spread out through space, existing in multiple places simultaneously until observed. The equation worked. It matched experiments. But it is strange, describing particles through abstract mathematical objects called wave functions. Then, 2 decades later, Richard Feynman offered a radically different picture. Same predictions, same experimental success, but a completely different way of thinking about what particles actually do. His insight began with a simple question. 1. When a particle travels from point A to point B, how does it get there? The classical answer is that it takes one path, the path that minimizes effort, the path of least action. This principle goes back centuries. Objects in nature seem to be lazy, always finding the most efficient route. Feynman asked a different question. What if they are not lazy at all? What if they explore every possible route, all at once? To understand Feynman's insight, we need to revisit the most famous experiment in quantum physics, the double-slit experiment. Imagine a barrier with 2 narrow slits cut into it. Behind the barrier is a screen that records where particles land. Now fire electrons at the barrier, one at a time. If electrons were tiny bullets, you would expect 2 clusters on the screen, one behind each slit. The electrons that pass through the left slit hit the left region. The electrons that pass through the right slit hit the right region. Simple. But that is not what happens. Instead, the screen shows an interference pattern, alternating bands of many hits and few hits, exactly like the pattern you see when 2 water waves overlap. Peaks where the waves reinforce each other, troughs where they cancel out. Now here is the disturbing part. This pattern appears even when you fire electrons one at a time. A single electron, all by itself, somehow creates an interference pattern, as if it passed through both slits simultaneously and interfered with itself. How can one particle be in 2 places at once? This is where Feynman enters the story. He said, "Stop asking which slit the electron went through. That question has no answer in the quantum world. Instead, recognize that the electron explores all possible paths from source to screen, including paths through the left slit, paths through the right slit, and paths that zigzag between them." But here is the key. Feynman did not just wave his hands and say, "Particles take all paths." He gave us a precise mathematical recipe for calculating what happens. Each path, every conceivable trajectory from A to B, gets assigned a tiny arrow. Think of it as a clock hand pointing in a specific direction. And The direction of that arrow depends on something called the action of the path. The action is, roughly speaking, the total energy expenditure along the route, calculated by integrating the kinetic energy minus the potential energy over time. Every path gets an arrow, every single one. The path that goes straight from A to B, the path that loops around the moon first, the path that spirals through the galaxy before arriving. They all count. Now comes the summation. To find the probability of a particle arriving at a particular destination, you add up all these arrows. Not the lengths of the arrows, but the arrows themselves, tip to tail, accounting for their directions. And something remarkable emerges from this summation. Imagine you are adding up arrows for all the reasonably straight efficient paths from A to B. These paths have similar actions, which means their arrows all point in roughly the same direction. When you add them tip to tail, they reinforce each other. The arrows line up. The total gets longer and longer. Now consider the wild paths. The one that detours through Jupiter. The one that spirals backward in time. These paths have vastly different actions. Their arrows point in random directions. When you add them up, they cancel out. One arrow points left, another points right, another points up, another points down. The total goes nowhere. Stop. Daddy knew. Think about that for a moment. Well, the classical path, the path of least action, the efficient route, emerges not because the particle only takes that path, but because that path is the only one that survives the cancellation. The particle really does explore every possible history, but the histories interfere with each other, and interference destroys all the crazy paths, leaving only the sensible ones. This is how Feynman explained why baseballs do not noticeably quantum tunnel through walls. The action for a baseball-sized object is enormous. The arrows for different paths spin so rapidly that neighboring paths cancel each other almost completely. Only the classical trajectory survives. But for an electron, the action is tiny. The arrows turn slowly. Neighboring paths can reinforce each other even when they are quite different. Quantum weirdness has room to breathe. Now, you might be thinking, this sounds like a mathematical trick, a clever way to calculate probabilities. Does nature really work this way? Here is where it gets profound. Feynman showed that his sum over histories is exactly equivalent to Schrödinger's wave equation. Same predictions, every time. And when physicists extended quantum mechanics to include fields, to describe not just particles but the electromagnetic force, and the strong nuclear force, and all the other fundamental interactions, the path integral went with them. Instead of summing over all possible paths a particle might take, they sum over all possible configurations a field might have. Think about it this way. A quantum field fills all of space with values at every point. A particle is just a localized ripple in that field. Where a particle might travel this way or that, a field might ripple here or there in countless different patterns. The path integral says you have to account for all of them. This is how physicists predict outcomes at the Large Hadron Collider. They write down the action for the known quantum fields. They calculate the arrows for every field configuration connecting the initial and final states, and they add them up. The procedure is extraordinarily difficult in practice, but the principle is beautifully simple. Sum over all possibilities. In fact, physicists at CERN are so proud of this approach that the gift shop sells a coffee mug displaying the equation for the action of the standard model. It is the key ingredient in the path integral, the blueprint for adding up all of reality. But here is where it gets interesting. The mathematics only works smoothly when you play a strange trick. You have to make time imaginary. That sounds like nonsense, but it has a precise mathematical meaning. Instead of using regular numbers to represent time, you use imaginary numbers. Numbers that, when squared, give negative results. In this imaginary time realm, the wildly oscillating arrows become calm, well-behaved exponential. The infinities become manageable. The calculations become possible. Stephen Hawking relied on this imaginary time version of the path integral to study black holes and the origin of the universe itself. He used it to argue that time began at the Big Bang and to count the quantum states hidden inside black hole horizons. And now, the boldest physicists are attempting the ultimate path integral, one that sums over all possible configurations of spacetime itself. Not paths through a fixed background, but all conceivable shapes the fabric of reality could take. This is the quest for quantum gravity. Einstein showed that gravity is really the curvature of spacetime. If spacetime is a field like the others, it should have a quantum nature. And if it has a quantum nature, the path integral should apply. We should be able to sum over all possible spacetimes, all possible universes, and discover why our particular universe has the shape it does. The mathematics here is ferocious. Nobody has fully tamed it. But the dream remains. Reality as the sum of all possible realities. Let us return to that disturbing statement from the beginning. You are right now walking through walls, orbiting Jupiter. And witnessing two of these summons. I should treat to Saturday gas, traveling backward in time. The sum over histories says this is literally true. Every possible history of every particle in your body contributes to your present existence. Most of those histories cancel out. The arrows point in opposite directions and destroy each other. What remains is the coherent experience you call your life. But the other histories are not nothing. They participate in the calculation. They enter the sum. Without them, the mathematics would give wrong answers. Does this mean alternate realities exist? That is a question physics cannot yet answer. What we can say is that the formalism which best predicts our experiments treats those alternatives as real contributors to what happens. Feynman himself was characteristically modest about the interpretation. He said, "The path integral is a way to calculate. It works. Do not ask me what it means. But we can ask, and the asking is part of science." Consider what this tells us about causality, about fate, about choice. When you decide to turn left instead of right, classical thinking says one path becomes real, and the other does not. Quantum thinking says both paths contribute. They both matter. The arrow for turning left and the arrow for turning right both enter the sum. One might dominate the probability, but the other is not erased from the mathematics of the universe. This is not a get-out-of-consequences-free car. At the scale of human decisions, the classical path dominates overwhelmingly. Your choice is effectively unique. But at the deepest level, the architecture of reality seems to include all possibilities, weighted and interfering. Think about what it means for the universe to be, as the physicists say, the sum of all possible universes. Every timeline that could exist, every configuration of matter and energy, every arrangement of stars and galaxies, all summed together with interfering arrows to produce the one reality we observe. We live in the interference pattern of infinity. There is a famous Feynman quote where he says that if you think you understand quantum mechanics, you do not understand quantum mechanics. He was not being humble. He was being honest. The sum over histories gives us a way to calculate. It predicts experiments with astonishing accuracy. It unifies quantum mechanics with the principle of least action that governs classical physics. It extends seamlessly from single particles to fields to, perhaps, space-time itself. But it does so by telling us that reality is stranger than any previous generation imagined. That determinism fails not because the universe is random, but because it is extravagantly multiple. That the path you are on right now coexists in some mathematical sense with every path you could be on. Feynman found this beautiful. He loved that the universe did not owe us a simple story. He loved that the truth was weirder than any fiction. And perhaps that is the deepest lesson. Not that physics is difficult, though it is. Not that nature is mysterious, though it is. But that the universe rewards those who ask honest questions with answers more magnificent than they had any right to expect. You started this video believing that particles travel on single paths. You end it knowing that they explore all paths. That reality emerges from the interference of infinite possibilities. That the world is not a story with one plot, but a symphony of all possible melodies playing simultaneous. The next time you walk across a room, remember, you are also walking through walls, orbiting Jupiter, traveling backward to the moment of your birth. The arrows just happen to add up this way.